Thank you everyone for coming. My name is Daniel. This is the webinar about HPC workloads in the cloud. And before starting, I would just like to introduce a few slides about ENCCS. And the ENCCS is the National Competence Center in Sweden, and it's hosted as a partnership between RISE and Linköping University. And what we do is to aid industry through HPC access, trainings, and giving support, including consulting or developing proof of concepts together, and so on. And each country within the European Union and even outside EU, like Turkey and the UK. No, UK doesn't have, I guess, but they have their own national competence center who has similar functions as us. We focus on HPC essentially. We collaborated with many companies so far, so you can see here there's a lot more than these ones. If you want to see some case studies, you can go to our website. And if you are in a startup or a company or even a small medium enterprise, you can talk with us if you need help in some way regarding your workload. We provide trainings. So if you go to our website, we have many trainings that you can go through self-learning or by attending our virtual trainings, both in person, virtual. So we have about GPUs, Git, Quantum, and so on. And for example, next week we have a webinar on Quantum. We have a very interesting event on 22 of this month with the North HPC Summit, with also a workshop from AWS that relates strongly to this webinar. So it's a lot more practical and lots of speakers from industry. So if you are around in Stockholm on 22, you can register and then it's free. And you also get access to the parallel events that are also happening on the same place as the North HPC Summit. And on November 3rd, we have the Quantum Autumn School. If you are also interested in quantum, you can join us for an entire week and participate. And my last slide about ENCCS is that there is also a blog post on our website about a similar topic in this webinar that you can read a bit and see what to consider when migrating from HPC to cloud in terms of resources, politics, what you need to take in consideration overall. So there are many things that you can consider, and it's food for thought essentially. So yes, and the webinar starts from now on. If you have any question, feel free to write in the chat. I cannot see the chat right now, but Francesco or Yongle, the moderators, they can interrupt me if they feel that it's the moment to interrupt, or we can just take it at the end as well. The webinar, the content of the webinar, the topic of the webinar, apologies, is very broad. So I try to have some focus points here, and I maybe it will be some parts will be interesting to some parts will be interesting to others. And yes, we can start about that right now. And I always show this slide to most of presentations I make about cloud computing and HPC. And this is because when you evaluate cloud computing, you need to understand what they run. And the applications that they usually run, the user-facing services in most cases, they are built for reliability, for example. So if you have Nginx on the bottom right, it's a web server, and if one of the servers fails, you still need to have it providing the service to the user, so it can still be up and running. It's what we call loosely coupled workload. Same for Cassandra, Same for Redis, that are both database. One is in memory, the other is not. And full applications in cloud computing, they are very microservice based. They are often microservice based, in many cases. So if you see very big companies like Spotify, Netflix, Twitter, they have many microservices, both for maintenance aspect for maintenance to help the code base, and also because the software architecture, the software engineering architecture for user-facing workloads also makes sense, because you always need to keep you always want to keep the service up and running, so need to be a bit fault tolerant as well. In contrast, HPC workloads, they are often tightly coupled. And I say often because there might be HPC applications that are loosely coupled, like the cloud ones, but I might not have seen them yet. So because every day you have an application and so on. And by tight coupled, I mean that's a design choice that usually maximizes performance, because we run HPC workloads in our on-premise cluster, and by doing that, we have to do a lot of compromises. So, for example, most of the applications, the ranks are interdependent between them. So the default behavior of an MPI application is that if one rank fails, all the others will die. So this is a bit harder to deal with, and it strongly contrasts with the cloud ones. And another aspect that we need to take into consideration when comparing cloud and HPC is how the resources are allocated. So if you have a high performance computing system, like the ones in Linköping, or the one at KK Dardel, or in Umeå, or whatever place, you usually get all the resources for you. So you wanted to allocate one node, you get the entire node only for you, and you do whatever you want with that. In cloud environments, this is not necessarily true. It might be the case that you get a full node for you, but more often than not, you might be sharing the same node with other clients. So you can have 2 CPUs, the other can have 3, another can have 1, and so on. So you care more about the resources existing than the location where they are. So yeah. And if you compare schedulers, especially Slurm and Kubernetes, for example, and I'll talk more about Kubernetes later in this presentation. When you allocate a resource in Slurm in a high-performance computing system, it's often expected that the resource provisioning will stay stable, so it won't change. You allocate 8 nodes, you run on 8 nodes, even if you don't use 8 nodes. And that's a bit of wasted resources in such cases. And if you want to change, you might often see yourself going into the queue, having to wait, and so on. Meanwhile, if you use a cloud orchestrator like Kubernetes, it has the ability, you can configure it itself to scale according to the demand. So if you are running the web server, you have during the day you receive a higher influx of users. Then this means that you might need more nodes or more pods or whatever other resources to support this amount of incoming requests that are arriving. And at night you can just remove that, and it is usually a no-brainer. It works just well. Since we're talking about cloud computing, we have several service models that we need to discuss. And if you see these images in other places, they usually would go traditional on-prem. They would have the infrastructure as a service, the platform as a services, and the software as a service. All the iterations, I mean. So this one from Google, they also established the containers as services and functions as services. I'll go through all of them by examples. So Or traditional on-prem is essentially, you can pretty much imagine a high performance system where you control everything. When you have infrastructure as a service, this means that you are running essentially a virtual machine on someone else's hardware. So you can do whatever you want. You can choose the flavor of the OS. You can run you can run whatever software you want there, and singular. Containers as a service. Imagine that you have a container, a Docker container, and you just want to rent the Kubernetes or Nomad infrastructure to run that container. But still, the configuration of the Kubernetes is still on you. So you need to set up all the infrastructure for that. So if you know Amazon or Amazon Elastic Kubernetes Service or Google Kubernetes Service, GKS, it's the equivalent for this. And if you go to the platform as a service, you take even one degree further. And you essentially don't even need to worry about the underlying infrastructure. You don't need the Kubernetes. This is mostly managed by the provider. So of course you pay more, but that's the price for ease of use. And the function as a service and software as a service, they're not really relevant to us right now. But essentially, if you want to run a serverless application or a user-facing service directly, it's the models that you would choose. And the major question that usually appears when you discuss HPC and cloud is why? Why would you want to run your HPC system, your HPC workload on the cloud if it runs so well on HPC systems? And the reason is essentially cost. So you don't really compare performance. It's usually comparing apples with oranges. There are some pros and cons regarding performance, but cost is really a field of study that you can often find in many papers. In some cases, the cloud can be better than HPC if you consider some specific CPUs, virtual machines, services, and so on. I didn't see any study comparing GPUs with GPUs as of now, because we have this AI boom. But imagine that if you are a small company and you want to run your R&D workload, you cannot buy a HPC system for yourself. It's just the upfront cost is too expensive. So you go to the providers and see what they can offer, because many of the major ones, and but AWS, Google Cloud, and Azure, because they're three biggest, but you also have on Europe some of them like Scalaway, like OVH Cloud, or even China with Alibaba. They also have many offerings targeting high performance computer workloads that you can execute. So you go there, you execute from how much time you want, and then that's it. You don't need to worry about the infrastructure anymore. So this is a very good point. For others, like it might be worth to have the infrastructure. So many oil companies, they have the our infrastructure because it makes sense. So in Brazil, we have this company called Petrobras, which is a oil company, and they need to process terabytes of data, of seismic data. And for them, since the cluster will be up and running all the time, and they also have some worries about the data and so on, then it might make sense to them to acquire a cluster, and they have one in fact. But even this case, like Microsoft Azure, they have a very famous case about a hybrid cloud where the data is stored locally in the oil company premises, but the processing itself is done at the Azure Microsoft Cloud. So there's a lot of very complex trade-off that you need to take into consideration when examining this. But reason number one is cost. The reason number two is usually the ecosystem. So the HPC is still a niche in the sense of the community is a lot smaller than the ones that exist in cloud computing. So by using the entire sorry, by using the entire by transitioning to cloud, you get access to many applications that are not necessarily available on these HPC systems. And there are also some custom silicons. So if you want to run on Google's TPU or Amazon's inferentia, you just can. And it's easier than doing an HPC system because HPC system is there and it will be forever the same system. Of course, they can upgrade and so on, but you don't really expect major changes or like these big providers they have. And now that we are talking about HPC workloads to cloud, we refer back to that image with the service models, and we compare all of them, how you can deploy the applications. So on the infrastructure as a service, you essentially have the hardware. You have a hypervisor that provisions the infrastructure that you want. And for every application that you can potentially execute, you would have to virtualize the guest OS, whatever you want from that, the dependencies, and also the applications. If we go to the container as a service or the platform as a service, for every application, these applications share the same Linux kernel. And by sharing the same Linux kernel, the natural overhead of having the full-blown OS virtualized over the hardware is lower. So you often get a better performance. So this is the two ones. The infrastructure as a service is essentially a provisioning virtual machine. The CaaS is Kubernetes containers and so on, which is the focus of the presentation, these two models. And on the left, you have the traditional HPC, where you just run on bare metal because you have often have the best performance, and that's how it is designed to be. And I mentioned that you have the providers they provide, the cloud service providers they provide many resources targeting HPC workloads. And for example, on Scaleway, you have the high-end CPUs. So here in this screenshot I took, they have some GPUs, and I saw that they also offer the Zen 3, the EPIC AMD EPIC processor for those who want. Wait, I think okay. I thought my phone went out. If you see the also Amazon and Google, if you don't want even to bother on transitioning on configuring your application to these service providers, they go as further as just to provide an entire Slurm environment within cloud. So all the nodes that you provision, they will be connected, they will be installed with Slurm. So you just go there and you run your script and it should be okay. So you don't even need to worry about the transition itself. Everything is more seamless. If you go to the also AWS, they provide this Elastic Fabric adapter for helping the connection between nodes. So they bypasses the operating systems for connection and lower the overhead of the interconnect. So you also get better performances. So there are many solutions that you can use on cloud essentially because it's being offered by the providers. And another advantage of the cloud is that you choose what you want. So you might not always need the top performance of CPUs or GPUs because maybe you're running a data generating workload and you want more storage. So you can choose more storage over the CPU. You can also choose the region that you want the virtual machine to be deployed. So in big providers, they will have all over the world to choose with different laws to apply as well. Also, if you are getting smaller, then you might have your own system. You can choose also your own operating system and so on. And just to, as an example, I put here a screenshot of Microsoft Azure provisioning. So you get to choose where it will be, the image to be deployed, and later on it's the options for disk, for networking, how you want the nodes to be connected, additional services for monitoring, management that you can often pay more, and so on. So when we talk about infrastructure as a service, the transition is often more direct, because you are on the control of the most of the environment directly. So you might get your application from Lumi, recompile the dependencies to your target system, and get your app, recompile and run. Of course, you might need to configure the network by yourself, which might be a bit more problematic, but it's a lot more direct. So yes, this is the very simple. What the issue with the infrastructure as a service is often when we talk about portability, and this is because in many cases you have the entire image that you with your application, with the OS and so on. And if you want to shut down your virtual machine, you need to save the state, and then you need to put all the image into a repository. And every time you deploy, you need to take that image from the repo and restart again, and so on. So it's a bit more problematic. And of course, there are solutions for that. So you can save all the data in a separate disk. You can use initialization scripts. So if you use it, if any one of you from academia ever used a Cloud Lab from the United States, it's a cloud computing service for academia over there. Then you can also create out the code that you want to be deployed. So I did for them for Kubernetes. So every time I started the virtual machines, 3 or 4, it would install Kubernetes by default, link themselves with all the dependencies and so on, which takes a bit of time as well. So a deployment usually took 40 minutes, and it was not even that complex. So portability is usually the major issue with the infrastructure as a service. So we have containers. And this is a really good reason why containers are so popular, is portability. Of course, we can talk about isolation, security, and so on, but portability is a strong reason why you would want to use containers. And when we talk about containers, they are based in a feature from Linux called control groups. So control groups is essentially able to isolate a process, and you can allocate the amount of CPU memory or even the CPU set that you want the process to use. So if you allocate 500 megabytes to the process, it won't go over 500 megabytes. It will die if it requests more. In CPUs, if it wants to use more CPUs, it won't be able to either. So security is a way to isolate the process. I'm not sure if there's a slide about that, but oh no, it's here also on this. But cgroups is a Linux feature, and naturally, when I talk about containers, I'm usually talking about containers on Linux, because if you go through Windows or Mac, when you use a container engine over there, it will usually be through a virtual machine that is virtualizing a Linux kernel somehow. So for example, on Docker, they use this version called Moby Linux, which is a very, very minimal distribution just to use C groups over there. So take that into consideration. And we have several container engines as well, that each one has a different approach. So in HPC environments, like Lumi, you often see mostly people talking about Singularity and Aptainer. They're not really the same thing. They're starting to differentiate themselves. But Aptainer is a fork from Singularity that is now managed by the Linux Foundation. Charlie Cloud, for example, is also used in the HPC settings. So you can find papers from NERSC using Charlie Cloud, but I don't see it very much popular. Docker and Podman are more common. Podman is compatible with Docker, and some people prefer Podman because this for security reasons. So Docker, it needs a daemon to build and to run the container images, while Podman doesn't. And so you can run Podman at user level, essentially. And since Docker is popular, we talk about Docker. And it's if you see the idea over that, is that you have several layers of image of several. A Docker image is composed by several layers, and these different layers they can be reused to avoid to save space, of course, and to improve reusability. So if you have a base layers, for example, the Debian Slim or Alpine Linux, and then you use apt-get to install wget or any other application like that. So any other images that you build based on Docker and has also the apt-get, they don't need to be rebuilt. They'll be already on cache and they can be reused. So that's pretty much what the image on the right says. You can save a lot. So you can use the same images to deploy different applications and lower your building time. And when I made image is that these container engines, all of them, like including Singularity and Podman, they have a procedural style of defining the image itself. So here we have the Docker image, and you see the first line is the base image from Debian 12 is Slim. So you want this image to be to be our base. And then we run apt-get to install applications. So we install dependencies. We build our application, and we have some configurations. So this is usually the flow when you are building a application image: dependencies, application, and post build. And you can run some scripts afterwards when you are deploying the application. Here we deploy GROMACS, which is a molecular dynamics application. But yeah, the downside with this approach is that images can be very big. So if you're building a very complex application, the compilation libraries might be different than the runtime libraries. So you can often have a simpler building process, not a simpler, but a smaller image by having what they call 2 or even 3 or 4, depending on how complex is what you want to deploy, with several stages built. So here we have an application that you originally compiled in the image one. So they call the image builder. It's a Go application, and then after they've compiled, you go there and you change you copy the executable to the image too, and you can separate everything, the environments. It's also better to do for software engineering, and you often want to use very small images. So in this case here, we use Debian Slim, which is a Debian version without the documentation and in some other packages that are not really relevant. But for them, many people use Alpine Linux, and Alpine Linux, if I recall correctly, the image is a few megabytes, so 30, 40 megabytes. So it really makes everything smaller and simple to be deployed. And for each image that you build, you build that for a specific CPU architecture. So you want to run a Docker image on your computer. It will first check if there's a corresponding architecture in the repo, and then it will be downloaded and executed. If there is no architecture in the repo or in your system, then it will just fail to execute. And a very interesting characteristic of this is that you can potentially use this feature to run heterogeneous HPC. So we have on the left side, we have this image for iPic3D I created, and you have both for AMD, for x86, for ARM, and for RISC-V. And there's some MPI feature that allows you to run the three of them together. So nothing hinders you to provision a cluster with the three different architectures, run the three different images with different architectures, and connect them. It's totally possible, and it's actually very cool because I did that. So yes, so this is a very interesting characteristic of the containers. And Docker is essentially designed to be ephemeral, not only Docker, but most containers. You can, of course, have what they call persistent volume. So the persistent volume will stay there even after you close the container, and you can mount this volume into the container. But the default behavior is to lose everything afterwards. And in Docker, if you start an application bin bash, the container will be alive while it's being executed. So after you do exit, the bin bash process will die, and then the container dies. So this is something to be taken into consideration. And you also pull the image from this Docker Hub registry. Just a curiosity, there are several container engines, but there are also standards that they need to be compliant with. So there is this OCI standard, open container interface, that the engines need to comply with, so they can interact properly with the Linux kernel. And there are several applications that are OCI compliant that container engines can make use of. But containers is that we have been talking here is only for a single node. So you essentially start a container, you run a single node, and that's it. And the question that you often want to run several nodes and also several containers in these different nodes. So that's why we have the figure of the containers orchestrators, and have Kubernetes, Nomad, OpenShift. There are probably others that I do not have in my mind right now. And Kubernetes is by far the most popular. So it is maintained by the Cloud Native Computing Foundation, and they run an annual survey about the usage of their products. So of course it's very biased. So, but if you see on the right side, Figure 10, then you can see that from 2023 to 2024, the amount of the companies and users using Kubernetes actually increased. And they usually send the survey to companies and relevant people, if I recall correctly. Also, on the Figure 4, it's also about usage of the HPC, the cloud systems. And you see that the public cloud is also very, very popular. So yes, this is a trend, and whether we want or not. When we talk about Kubernetes, Kubernetes is a lot. It's really a lot. So it's very modular. It has several components, and it's a whole package. And if you want to deploy Kubernetes, you have several distributions or flavors that we can say. Some of the flavors, they're like Minikube and K3D. They are often used for your personal environment. So you can just go right now and look for Minikube or K3D or Kind Kubernetes in Docker and see how it works in your own computer just to test. And it's actually meant to simulate these sort of environments. If you see Cube ADM and K3S, they are designed more for full-blown clusters. So it's actually expected that you have at least 3 nodes, and I'll talk about Kubernetes architecture later on. Wait a second. And you deploy there. It's a process. You configure the cluster and you just run. And other interactions that you do with the Kubernetes is usually through the application we call kubectl or kubecontrol, which then you can use to get what is running or to start new runs. And the Kubernetes, it also supports several clients. So if you don't want to use kubectl for whatever reason, you are building an application that needs to interact directly with Kubernetes for some reason, you can use Python, Go, Java, C, and several other bindings that they have. I think it's Scala as well. So it's very, very versatile because it's a huge project. And when we talk about Kubernetes, and like I mentioned, it's highly modular, we need to understand that Kubernetes cluster is at least three nodes. And I think here on the main image, node 1, but it's actually node 1, node 2. And for one of them, these 3 nodes is a control plane, which runs the essential features of the cluster. And the others are the worker nodes. You can have, of course, more than one control plane. So you can build what they call a high available Kubernetes cluster. So if one control plane is down, you can still have other running and checking everything. And all the components from the cluster, they can be changed. So you can change the scheduler, you can change the controller manager, you can change the API server to a custom version, because you can just remove them and then put whatever you want. And that's actually done by some applications that I will show later. When you start an application in Kubernetes, a container, it's usually often called pod. The pod is the smallest abstraction of resources within Kubernetes, and the pod encapsulates a container. The interactions that you do in Kubernetes is through the API server. So when you do kubecontrol command, you are sending essentially a command to the API server, or same if you do in Python or similar. And each working node, it has the kubelet that gathers metrics, checks if everything is working well, and sends back to the control plane for keeping check for the controller manager. The scheduler usually goes in 2 ways. So if you want to schedule a pod, it will check whether the node is not full, and then we assign it to the pod to a node based on the resources that you requested, and I'll talk about that later. Like I mentioned, it's highly modular. So if you run the kubecontrol command, kubecontrol get pods from all namespaces. So this means that we can see the system namespaces that you can see on the left, cube system. You see the API server, you see the controller manager, the DNS services that you can also replace, the scheduler, and so on. And some popular applications are Volcano, Prometheus, and Grafana. Volcano, and I think there's a slide after this one over there, or maybe 2 slides after, it has a custom scheduler and a custom controller manager that can help you to run MPI applications in Kubernetes. And I'll go in detail on that later on. Prometheus is a time series database that can store all the data from the gathered in the cluster, and you can query. And Grafana is a visualization tool that is also highly popular. There are several others, both to replace Prometheus, both to replace Grafana, and so like NetData is another popular one. Also, Volcano, you can also run API. Instead of using Volcano, you can run Kubeflow for AI workloads as well. So there are many solutions that you can find that you just use whatever suits you better, each one with your cons and pros. So this is just a slide to show some plots from Grafana that you can call. And the common thing is to also get application level metrics through the process they call observability. So you can scrap the data from the application, put it in Prometheus, and plot somewhere else. It's very common. And when we talk about Volcano, as I mentioned, it helps you to run MPI applications. And how does it work? The secret is that MPI it uses SSH. So you can start applications MPI through SSH. And Volcano, when you're starting Kubernetes in the application, Volcano can help you define a master and the working nodes for the MPI applications. The master runs the MPI exec command. So you can see it's exactly the MPI exec with everything. And the workers just runs SSH daemon. So it's waiting for the connections. And Volcano defines this variable MPI underscore host with all the IPs from the workers. So the master can reach each one of them and successfully connect. Not only this, the secret is also that they all share the same SSH key. So by sharing the SSH key, the connections are allowed, and then the application runs great. It just runs. And yeah, so Volcano has I won't discuss the Volcano architecture in the admission, controller, scheduler, but you need to know that this is the process that makes MP applications running possible. And to some extent, it's also the same process used in other operators that also runs MP applications on Kubernetes. If you want to run a Kubernetes object, so we have pods, but the pods, they are designed for finite for applications that run for a very long time. So the web servers that are supposed to be there forever, because they need to be always serving the user. So this is the sort of a application that the pod type is designed for. And upon the pod type, you have deployments, demo sets, and the others. So the deployment, for example, it allows you to keep a certain amount of pods always online. So if one goes down and you say, oh, I need 5 hours, and it will just restart and keep 5 pods online and so on. You can also do rollouts. So if you want to run a new version of application, it can make one down, one up, one down, one up, one down, one up, and so on. However, if you are talking about HPC applications, we have another type called jobs, which is designed for the finite run applications. And there's a slide also showing how it is different. The relevant thing in here is that when you deploy an application, you can choose the amount of resources that you are allocating to that pod. So here we are putting 128 megabytes and 250 M, and the CPUs are not defined in it's defined like it's not entirely valid. You don't need to assign 1 core, 2 cores, 3 cores, but you assign how much time that will be the application can use from that CPU. So in here it's using 1/4 of the time as a request. And there's a difference between requests and limits. Request is more about scheduling. So if you want to schedule this pod, the node, it has to have at least this amount of resources available to be scheduled there. But the limit is the actual hard value that the application cannot go over. So if the application requests more than, it's actually wrong, it's 128, more than 128 megabytes for the MB bytes if it requires more than 120 MB, it would go out of memory, it will die. So this is a very hard limit. On CPU, the applications don't die, but they get a lot slower if they need more. And this slide here is just to show how it changes the YAML. So you always have, for all the objects, you have the API version, you have the kind, you have the metadata, and you have the spec. And usually what changes according to the kind that you put here is the spec. So here I can also say that if my job gets problem, it can restart if it fails. And that I should always pull a new image because I might update it and so on instead of using from the cache if it exists. So this is the gist of that. A final thing, and I won't go much in detail with that because I have only 10 minutes left and I hope to cover everything in 10 minutes, is that the networking model. So every pod in Kubernetes, they get their own IP, and they can communicate between other pods without much issue. You can also have a DNS server running Kubernetes, so you can have names for the pods that you can access. But you cannot access this network from outside the Kubernetes cluster, and for that you need to deploy what they call a service with a load balancer and that accepts some connections from outside. This needs to be configured properly. And this is the next section of the webinar, and this is about the actual workflows. So as I mentioned in the very beginning, you get access to a lot of different tools that you can use in the cloud computing environments, and one of them is these workflow ones. So here we have. I will talk about Airflow because it's quite popular, but you have Luigi, Dagster, and Luigi I think it's maintained by Spotify or was maintained. Dagster is also so popular. You have AWS Step Functions, which is has similar ideas, but it works a bit differently. And you have these three: Nextflow, SnakeMake, and I forgot the name of the big one that is also used in mostly molecular dynamics, if I recall correctly. And if we're talking about Airflow, we need to first talk about which a DAG, a direct acyclic graph. And the DAG is essentially a set of tasks that are not that has a started and the end. So here you have a proper DAG. and there's not much mystery about that. You see that task 1, task 2, task 3 has a requisite of task 1, task 2, and the final task is only executed after the 3 others are also executed. And on Airflow, this is how you define this is how you define the workflows on Airflow. And you can put Airflow on Kubernetes. It has its own architecture where it stores all the DAGs that you want to run. It provides a web interface for you, so you can just press a button and start running if you want. And for each DAG that you create, it will assign the pods to the nodes and run properly according to what is needed. I have an example here, which is a work I did a few years ago about molecular docking. So molecular docking is a process used in the drug industry for essentially finding where the proteins can be put together with a ligand, which position, and so on. This is used for development of drugs, for example. And it's often a process performed in HPC systems, and we migrated that to the cloud using Airflow. And this is sort of the DAG that we established, the amount of tasks. So you consider that to perform the docking, the process itself, you have the ligands and you need to have the ligands and receptor, and each one of them has this own task to be assigned. And if you see the code, it's not the script is not full. Internally, I think it's 100 lines or something. But for each task, we created you interacted with the Kubernetes pod operator. We are executing a shell script within the container that we developed, and we define it right on red what is the order of the tasks. So performing docking is having the 2 dependencies, receptor and ligands, and finally you have the post processing after the docking process. The advantage of this is that in a traditional workflow that you are not using any workflow management system, you usually do the full ligands before starting the docking process itself. While when you are using a workflow management system, especially on cloud, it makes it easier to have the tasks running parallel. So when you have enough receptors and ligands, then you can start the docking process and do it in parallel. So you can save a bit of time, and thus also a bit of money if depending on where you are running. Another interesting thing, workflow, this is from a paper, this is not mine, but it also integrates Airflow with different HPC systems. So in this case, they are running our Earth observation workflow, and you can see here how it is. And the Airflow in the cloud, it interacts with 2 different high performance workloads machines. So it also works reasonable. And we don't really discuss performance because it's sort of hard to compare what you are running against or what you want to compare the performance with. But by having this sort of systems, you can be more smart about the resources that you are using, and this is really, really important. This is the last slide, and conclusions that using HPC workloads means that there is a curve to be learned, but you get access to many tools that are not commonly available on traditional HPC systems. And if you are in a company, this can also mean that you can potentially also save some money by running there. But yes, I think this is the last presentation, and we take some questions. I did right on time. It's 1 right now. Thank you very much.